Hi and welcome to the Wireless Communication Project presentation. I am Arun Raghunathan and I will give you a quick view of what my project is. Today we will see about optimal resource allocation in OFDMA systems with user rate constraints. Demand for wireless connectivity is on a steep increase throughout the world. Larger and larger sections of the population are using wireless services and more such services are being offered, leading to increase in competition between service providers and thus higher data rates at lower prices. Newer techniques to efficiently utilize available resources of power and bandwidth are constantly being developed. OFDMA is an efficient technique to provide services to multiple users. This project is concerned with optimal subcarrier and power allocation for OFDMA systems. I have developed an algorithm for optimal subcarrier allocation followed by a variant of water filling algorithm. The objective of these two algorithms is to achieve maximal total capacity of the OFDMA system with proportional rates while maintaining fairness among the users. And the aim of this project is to efficiently allocate subcarriers and power in OFDMA systems so as to maximize the overall capacity of the system. And the motivation of the project is the growth in wireless systems with more personal connectivity has led to increased data rate requirement and increase the number of users. Bandwidth and power being the valuable resources have to be allocated optimally so as to achieve maximum overall capacity of the system, while fairness has also to be maintained. I have developed a mathematically fundamental algorithm for efficient subcarrier allocation and a simplified water filling algorithm. So here you see the graph for the OFDMA. What is OFDMA? It is a multiple accessing version of OFDM. And what is OFDM? It is the available bandwidth divided into many narrowband subcarriers using inverse fast Fourier transform or the fast Fourier transform. And OFDMA is to allocate subcarriers and powers to users. Here you could see a few advantages of OFDM or OFDMA. It can easily adapt to severe channel conditions without complex time domain equalization. It is robust against narrowband co-channel interference, and there are many more. Here you could see OFDMA downlink model. What I have considered is an OFDMA downlink which consists of blocks per bit, subcarrier and power allocation, and IF50 and cyclic prefix, besides the channel gain estimation blocks for each user. I assume that perfect channel state information, that is CSI, is available. In practice, however, the availability of perfect CSI is seldom the case. The imperfect CSI case is also treated elsewhere. If there are k users and n subcarriers, the CSI is contained in k cross n channel matrix, which is the H. The system model can be described as shown in the figure. The subcarrier allocation, which is C of k comma n, is equal to 1 if user k is on the subcarrier n and it is 0 otherwise. Our objective is to distribute the subcarriers and total power P total efficiently among users to maximize the total capacity, whose formula is given below, and that is here. And now first let's see about the subcarrier allocation. Among that we will see about the Wong method, that is the Wong algorithm first. Initially we have a SASO system, that is the single input and single output system of k users and n subcarriers which are to be allocated to those users, which is denoted by k cross n. The gain matrix, which is the H, which is denoted by k cross n, is generated first. The algorithm proceeds in a way such that for each k from 1 to k, n for which H of k comma n is maximum is found. That subcarrier n is allotted to k, that is each user gets one subcarrier in the first iteration. Then calculate R of k, which is as given below. After that we have to repeat the following steps till all the subcarriers are allotted to each user according to their requirements, and those are first find k for which this value is maximum. After that, for this value of k, find n for which H of k comma n is maximum. Then allot the subcarrier n to that user k, which is k, and decrease the value from that corresponding n of k, that is n of k minus 1 for that k. After that, compute R of k again and repeat the steps above until all the users are allotted with their share of subcarriers. The maximum capacity of the system is achieved only if each subcarrier is allocated to the user with highest gain on that subcarrier. but the rate proportionality makes this high capacity impossible. So, as some users with high gains on all subcarriers may require only a low proportion of the total capacity, and low gain users may have high proportionality. So, in one subcarrier allocation, the disadvantage is that a subcarrier may sometimes be allocated to a user with low gain. The following example actually illustrates this. You could see that now by Wong's method, fix user 1, the highest would be 0.49, which occurs in the column 4. Now 4 is assigned to user 1, but you could see that user 2 has a higher gain of 0.45 on 4 than user 1 actually. This is a suboptimal allocation actually. So thus we have developed a new algorithm which improves the total capacity of the system. Now moving on to the new algorithm. For this we search over each subcarrier from n is equal to 1 to n to find which user has the highest gain on each subcarrier. Let n of k be the set of subcarriers for each user k, and these subcarriers are those on which k has the higher gain than all the other users. Now denote the subcarrier sets as shown here, where the set contains the subcarrier indices for that user k. Now sort the H matrix column wise, that is in descending order, and find the 1 cross n test array given by the difference between the first and the second rows of the sorted H matrix, that is the difference between the highest and the second highest values in each column of the H, which is something like this. And now let this be the number of subcarriers in n of k. Find that k for which n of k is maximum. Now for that k, definitely there would be this relation, and this fact was arrived intuitively and was found to be correct during simulations. Now that k is fixed for every n belonging to n of k, the corresponding values in the test array are examined to find maximum in the test. The subcarrier n for which the test of n is maximum is allocated to that user k. This process is repeated till user k gets nr of k subcarriers. Now user k is taken out of the equation, that is by making the kth row of h all zeros. Now there will be some more subcarriers in n of k which are unallocated, and this will be taken up by other users. The purpose of the test array is to ensure that by giving up unallocated subcarriers to other users, we are not losing too much gain. Only those subcarriers for which the test of n is minimum are taken up by other users. The above process is repeated until all users get their share of subcarriers. Now that the subcarrier allocation has been done, the power allocation algorithm, which will be presented shortly, can be applied for the power. I generated 1000 different channel realizations and varied the number of users from 2 to 10 in steps of 2. I obtained two results actually. First by using Wong's and my subcarrier allocation algorithm separately, and using my power allocation for both methods. And the second type is using Wong's subcarrier and power allocation, and then my subcarrier and power allocation. While in the first case the improvement in total capacity was marginal, the improvement in the second case was considerable actually. Now moving on to the power allocation. Given a particular subcarrier allocation, maximum capacity is achieved by allocating power using the water filling algorithm, which is explained in detail in the report. An alternative water filling algorithm is presented here. We first find the water level W, which is given by this formula, and then the power is allocated as shown in this formula. After these two, power is allocated on a per subcarrier basis. The power allocated to each user is given by this particular formula. Then the total data rate of the system is thus found to be this formula which we saw earlier, and the result with the power allocation. Now moving on to the simulation result. The total capacity, the minimum capacity, and the delay graphs were obtained for the two cases as mentioned earlier. Let me just tell you how to execute my program here. And this is the MATLAB code. Here in the main program, I use the subcarrier allocation type 1 and the power allocation, which would be the same for both the cases. And in my main 2, I will be using my subcarrier allocation algorithm number 2, and the power allocation would be the same as before. So let me just execute here, and after execution you could just see that I'll be getting the two capacities, and the same goes for here. You couldn't see anything here because I just used these values to gain the plots which I will be showing you now. So I just have the values here, and let me show you my plots. So these are the plots. Before that, let me explain the input values that I gave here. So for now, the k range would be from 2 to 10, incrementing by 2 for each values. After that, the total number of subcarriers would be around 64, and the bandwidth is 1.25 megahertz, that is here, and the noise spectral density, I just assume it to be minus 80 dBm per hertz, and the maximum bit error rate, that is here, I've given it as 10 power minus 3, and so on and so forth. So by doing so, I just showed you the results that I got. I've plotted all those results. Let me show you the plot, and these are the plots. This is for where the Wang and Nu differ only in subcarrier allocation. You could see that they only differ in the subcarrier allocation, that is in the case 1. This is the minimum capacity, whereas this is the total capacity here. Now in the this is the plot I get for this delay plot that I get for the case 1. You don't see there is much of an improvement here, but this is the case 2, where you could see this is the total capacity, and the same case 2, and here you could see the minimum capacity, and in the delay you could see there is a slight improvement when compared to the previous one. Yeah, there is a lot of improvement here actually. So these are the plots. Now moving on to the complexity analysis. The detailed complexity analysis is given in the report. You could just go through the report for the each stepwise complexity analysis that is given for the order and other stuff. Those are detailed in the report. You could just go through the report. And while the complexity of the new subcarrier allocation is higher than that of the Wang's, it offers an increase in their total capacity. The new subcarrier allocation just aims to find the optimal combination of user subcarriers so that rate is maximized at a mathematically fundamental level. That is, there is no need to calculate rate at each step, and there are also some other advantages. Thus, we are sure that it will hold good against other subcarrier algorithms. That is purely in terms of capacity maximization, not in terms of complexity. Now moving on. The further work that could be done using this heuristic is that first let me say this project was developed as an algorithm for efficient subcarrier allocation in OFDMA systems, in addition to the development of a water filling algorithm with few mathematical operations. This work focused on a SISO, that is single input and single output systems, whereas MIMO wireless systems, that is multiple input and multiple output wireless systems, are gradually being implemented today, and the proposed heuristic can be tested to allocate resources in MIMO OFDMA systems and compared with those algorithms actually. So that is the further work that could be done using these heuristics, and these are the few references that I used to do my project. Hope you like my explanation, and hope you like my project. Please give me a like, and thank you for watching the project presentation. Thank you.